This is welcome to, the real life example within the introductory module to the data science and the real life example on fraud detection. So in the previous lectures, you had covered many concepts. Thanks to Subodh, you had covered frequentist views of probability. You had understood what estimators and bias were, some sample variance. You have introduced the single most important probability distribution function in all of statistics. You've been introduced to it, and you've learned what independent probabilities are, also conditional probabilities, likelihoods are, and finally you have been introduced to this thing called Bayes theorem, which is really one of the foundations of statistics. And we have applied these concepts to understand COVID-19. In this lecture, or in actually the coming two lectures, what we will do is we'll apply some of these concepts to the ubiquitous problem of fraud detection and prevention. These methods that I'm going to talk about are, they are part of your everyday life. Many of the services you use have them in the background, running and keeping your money and your whatever you're buying and selling on the internet, your identity, etc., safe. But in the process of introducing how these things are done, another thing that I wish to do is introduce you to basic data structures. So things like lists, arrays, stack, queue, because with a conceptual example, I'll tell you why these things are important. I'll also introduce you to beginning with just the elements of programming required for data science, not in a programming oriented way, but in a data visualization and data structures way, by using something called Google Collaboratory. So what I'm going to do is I'm going to show you right away how you can run a Python notebook online using Google Collaboratory. So to get there, what you should do is you should just type and you will get there, the first link. And since I am already logged into my Google account, it is showing me all the notebooks that I have created earlier. You can log in with your Google account and click on New Notebook, and you will see an environment like this into which you can type code and you can run it. It is Python code, but it is different from a regular Python environment in the sense that it is extremely interactive, so you get to learn things. I will be using a notebook that I have already made to introduce concepts to you. So, and then towards the end, so after we have introduced you to some of these things, I'll talk about types of errors in hypothesis testing. This is very related to what Subodh has already taught you in terms of false positivity rates, false negativity rates, etc. But we will talk about it within the context of our example. And then lastly, I will introduce qualitatively what a cost function is, because in the end, almost all applications of data science in including to machine learning, etc., you will find that it is optimization of a cost function. That is the final goal. So we'll construct an example, and we'll find using in which we'll apply concepts of the types of errors, and then we will construct a cost function for it, and I hope that will be pedagogical. So fraud is, every day it is now ubiquitous, sadly. It's unfortunately very normal. Federation of Indian Commerce and Industry, I think that's what FICI stands for, estimates that something like 4 to 5% of all revenue for businesses in India is lost due to fraud. Price Waterhouse Coopers, which is it's like a it's like a survey company and an auditing company. They had done a study of 9,000 companies in 2015 or so, and they found that more than 70% of the companies reported they had been victims of fraud. And there are many types of fraud. For example, there is credit card fraud, which is the example we will take up in this lecture. But for example, the Indian Railways loses about 1,300 crore rupees to ticketless travel every year, or at least of 2016, that was the amount. They also make something like 690 crore due to fines, which is for ticketless travel, and also maybe other offenses. But a portion of the fines is due to ticketless travel. So then the question is, how do you target your ticket collector? Which compartments does he visit to catch maximum the people who are traveling without tickets? Because he cannot obviously check every compartment. The general compartments, etc., are often very difficult to thoroughly scour. So there is an optimization problem there, and where using data can be helpful. Electoral fraud, which thankfully it's not widespread in India. We are still a functioning democracy, but you may have heard about this, that Myanmar just less than a month ago, maybe, had a complete coup wherein they were having an experiment with the democracy. They recently had an election, and then there was widespread claims of distrust in the election. It is not true to any of us. It is not clear to any of us if those claims that the elections have been rigged are true, but because such claims exist, there was a coup and the democratically elected government was thrown out. So faith in your electoral system and an ability to prevent electoral fraud is a fundamental aspect of making a democracy function. You can find similar examples, for example, in Egypt, etc., where they had elections, but people didn't have faith in the elections, and that led to collapse of political system. So across all systems, many mechanisms are in place to detect and prevent. For example, one of the simplest things you would have come across is if you're making payments online, especially with credit cards, there is nowadays something called multiple factor authentication. So after you enter your card and the small number at the back, which is supposed to be like a password, it will usually ask you for a one-time password, which comes only to your phone at that time, or it will ask you for like a code from some card you may have, or a cipher key. In insurance companies literally have bodies to try and prevent fraud among them. One of the ways they prevent fraud is by explicitly checking the claim. So they will call up the hospital and ask if it is a health insurance claim, they will call up the hospital and ask if these treatments actually happen. But they cannot, again, it may not be straightforward for them to do so for every claim they get. So they need a way of targeting which claims to go by. In railways, of course, we have the example I mentioned earlier of ticket checkers, and in elections, especially in our system, what we have there is something called the VVPAT, which is it creates a paper trail of something that a voter can follow up on later, making sure that your vote as you cast and your vote in your final the count can be explicitly checked to be the same. But there are people post observers. There are recounts wherein you do the counting exercise for electorates over and over again to make sure the numbers are consistent. And all of this involves statistics, data science. Most importantly, if vote numbers for certain constituencies, etc., have been made up, there are ways you can check for that. And that will actually be one of our main exercises in the next lecture. So what typically happens in the case of examples we'll consider in today's lecture is in the case of when you're buying something on Amazon or so, or you're initiating a transfer of money using your UPI, Unified Payment Interface on your phone, or using your credit card. And what basically happens is, over the internet, the information you enter, your credit card number, your account number, and things like passwords are sent along with additional data that you have allowed the app to collect, such as, for example, the GPS coordinates. So if you're making this payment while you're in Pune, the latitude and longitude there is different from if you're making the payment while you're in Bombay. And so that additional information, you are not entering it in, but because your phone has a GPS on it and you have enabled the app with which you're making this payment to take that data, it is usually often clubbed along with your authorization request, and it is sent to the system. So in the case of UPI payments, the system is something called the National Payments Corporation of India. If it is a MasterCard or a Visa payment, these are servers of those companies, of MasterCard and Visa, etc. And they maintain what is usually called a relational database, and this is where the data structures that I'll introduce next come in. The relational database usually contain a list of all transactions before, but organized in an efficient way. And those people, that data accessed by a data science team, usually using their automated tools, which will allow most of these transactions to be executed, but it will, based on outliers, flag one or two of these transactions as potential fraud, allowing either more processes to be triggered, or for a human being to intervene, or for additional steps. For example, you may have noticed when you pay with credit card that often, sometimes for some amounts, etc., you only need to enter your credit card or your debit card and your the number. But for some other amounts, or maybe they're larger amounts, you need an OTP. And so those sort of conditional decisions are made using a system like this. The data science team often, for a minority of the transactions, the vast majority of them are processed in a purely automated way. But for a minority of the transactions, the data science team may use a sophisticated model, which will involve all the statistics that Subodh taught you in the previous lecture, and quite often also machine learning. So this is a rough schematic picture of how a cash transaction request proceeds. Some of the ways in which data are stored in a relational database are using data structures that I'll speak about now. The first of which is an array. An array, you can think of it, since many of you, when you introduced, had engineering or so backgrounds, you can think of it in math as a vector. But if you don't know what a vector is, you can just think it is a collection of numbers that are stored sequentially. And so an array has a length, which is the number of numbers. So the length of this array is 9. And it also has an index, which is, it will tell you the position of the array in which you should look to get a number. So the 0th index of this array has the value 7. The 9th index, the 8th index has the value 46. The 7th index has the value 96, etc. In some languages, programming languages, tools, because things that are used for data science are not exhaustive. As in, I do not know all of them. In some of them, this indexing starts with 1 instead of 0. So let me explain what I mean by that. I have opened my my collaboratory notebook here. These are just introductory statements to import tools within Python that will allow you to do some numerical Python as well as plotting later when we look at data visualization. But here is what is called a declaration of an array. So I have just typed this out, and now you can view the array. So this is one of the advantages of using a collaboratory notebook instead of typing out into Python on your terminal, that if you just type out a variable's name, you see what it actually is. You don't need to explicitly print it out, though you can also print it out. So if you do print, and it will just give you the same thing here. Whereas in a command line terminal, you literally you can do only print, because just typing a variable name is not sufficient. So I have assigned this array to this name of the variable. Now what I can do is I can access each of the values within the array using the index. So because Python begins its indexing with 0, I can access it here. You see 5. If I do, let's say, if I want to know what is the 4th element in the array, I type 4, and the 4th element in the array is, so 0th, 1st, 2nd, 3rd, 4th. You get 8. It's very predictable behavior. You can play with this. One of the advantages of Python is that it is a very, what is called, high-level language. So it comes with a lot of built-in functions. So for an object, which is an array like I have constructed, which is strictly speaking a list, I can see what are the list of available options by if I just press dot, you see that I get to see the list of possible things I can do with this array. And so you can, for example, do sort, because you saw it there. So you saw sort, you can do that, and the array is sorted. So now if you print the array out, you see that the order has changed. Earlier, you had numbers earlier which were larger than the numbers that appear later, but now it is sorted in a numerical order. The smallest numbers are first, the largest numbers are later. You can also have the option to, you can see, for example, if you just highlight, one of the advantages of collaboratory is that it will show you the list of options. So doesn't appear to be foolproof, but I believe you just saw it here. So you can use the option, for example, reverse equals true here, and you can do the same sort. And what you see is that it's been sorted in a reverse order. So if you're learning to code in Python, anyone plans to start, which you will almost certainly need for your later modules, or it need not necessarily be Python, but that is one thing that I'm very comfortable with. The best thing to start learning with is what is called a Jupyter notebook, and one of the best places to host it, because it is literally free for anyone who has a Google account, is Collaboratory. And the other advantages are things like this, that it is very interactive. It shows you what exactly are the options you have at each stage of programming through pop-ups like this. So what I now constructed is something called a one-dimensional array, because as you see, the index with which I can access every bit of data within this array is just one scalar number. So I'm using only one number here to get this number. To get this element of an array, I can use, instead of 4, I can use 5, I'll get 9. And so by just varying this index, I can extract all data from this array. That is, you can have arrays of arbitrary dimensions. So here I am constructing a 2-dimensional array so the earlier array was of length 5. Here I'm declaring a 2-dimensional array of dimension that is 5 into 5. That is, it has 5 rows and 5 columns. So a 2-dimensional array, you can think in terms of a table. So it's just the number of rows and columns. If you want to access different elements of this array, you need 2 indices, because it has 2 dimensions. So the dimensionality of data can be understood in terms of what you think of as dimensions in your daily life. For example, imagine you want to specify a point on the surface of Earth. You have to usually give a latitude and a longitude, right? Or if you want to specify a point on your floor, you usually give a distance from one edge and a distance from an edge perpendicular to it, and that uniquely specifies a point on your floor. So, and in both these cases I mentioned, you have to specify two numbers, and that is because both the cases that we considered were two-dimensional. That is, the surface of a sphere is a two-dimensional, what is called a manifold, a two-dimensional surface. That's what you can think of it as. And in data science, also dimensions work in the same way. The array is two-dimensional because you need to specify two indices to extract all numbers, extract one number from it. So 3, 4 is 0. Let's see what 2, 3 is. Hopefully that's 6. Well, maybe 1, 3. Yeah. Yeah, because this is the 0th column. This is the first column, like that. So by varying these two numbers, you can access all data stored within a two-dimensional array. You can actually construct arrays of arbitrarily high dimensions. You can have a 10-dimensional array, a 20-dimensional array, etc. And within programming, it is just an extension of this within data structures. You will just have one more square bracket with an additional index. However, they're not very intuitive to think about, right? For example, in 3 dimensions, it is still kind of intuitive because you can think of it as specifying a point in your room, but not on the floor. It could be off the floor. Then you need to specify the height also. And if you're measuring, I don't know, the temperature of your room very specifically, then to store that data, you need a 3-dimensional array. But within data sciences, because I have not come across too many examples with more than 2 dimensions outside of the sort of things that, for example, Subodh and I do, which is because we are physicists. Our data actually, come in arbitrary dimensions. But for the examples we'll consider for fraud prevention, the only you usually do not see arrays of dimensionality greater than 2 because they're kind of hard to imagine. So a 2-dimensional array is basically just it's like an array of arrays. You can think of it that way. If you were thinking of this in any programming language other than Python, I would also talk about where in the computer's memory these things are being stored. For example, if they're integers, each integers have a size of memory, and then you need to append a memory location by the size of the integer to get to the next index, etc. But in Python, you don't need to worry about any of this. All the memory management is done by the interpreter, and you only think in these abstract terms like the indices. So that is one of the other advantage. Let's move on to 2-dimensional arrays. So 2-dimensional arrays, you can think of them as having rows and columns. So like a table you see in an article or in a paper, and you need 2 integer numbers to extract all data from it, and you have to vary those 2 integer numbers. So just now that since I'm introducing Python or in collaboratory, and Python itself, because it is a high-level programming language, has things that are different from array called list. And what I actually showed you is technically a list, not an array. The difference is that in a list, not every element needs to be the same kind of element. So you'll notice that this is an integer, all of these are integers, but here there is a string, right? And here there is a not an integer, it's a real number, a floating point number, a fraction. You can think of it that way. So if you declare it that way, with a list, you can have data of different types. So let's see now, list 55 of 2. And you can get that data, but with 2,1, you will get the integer. But Python has a module explicitly for arrays called numerical Python, NumPy. So you have an array, and you can convert this list that you have constructed into a proper array. And once you do that, what happens is it interprets intelligently in such a way that this is list 55. I can construct now an array out of this list, and what now I have is an array, and it has, if you notice, everything is now a string, right? Even though this is an integer number, unlike in the earlier case where it was explicitly shown as a number, it comes with quotations around it because it is being kept as text. So text, a computer stores text differently from real numbers, and in an array, in a what we think of formally as a data structure of an array, every data type has to be the same kind of data. So because one of the elements was cat, which was a string, when you converted it into a proper array from a list, it took every other element and converted it into a string, including the fractional number. Now, how many of you are you familiar with concepts like data types, like integer, string, floating point, etc., or am I speaking jargon?
Yes, sir, we are aware of.
You are what? Hello?
Yes, sir. Yes, sir. I know. I don't know about others.
Okay. So, yeah. Sure. I'm only now thinking about it and realizing that maybe I should. Anyway, so I guess what you understand my point here. Within an array, so one, just coming back to the non-practical
Sir,
example, the
just
following.
sir, just to clarify, are you talking about the data type like ordinal data, nominal data, or I mean discrete or continuous? Sometime this type of data.
I'm
Data.
talking about data.
I mean, in the sense of this array, and I mean these values in like cat was it is a ordinal data, so it is a string.
I don't know
So,
what ordinal data and the other term you used means, but
uh,
yes, cat is a string in the example I introduced, while the
I
others
mean,
are in.
sir, it is ordinal means those are basically we cannot. These are not numerical values in the simple sense. They are categorical. I mean, so they
Sure,
are strings. Yeah, yeah. Okay.
sure.
ठीक है sir, that
So,
fine. ठीक
yeah,
है.
so in a list can contain data of any type, whereas an array, everything has to be the same type. And uh, that is basically what I wanted to just show you. But these are all differences that exist only, for example, in Python by default. In C++, you cannot have any kind of array-like structure which contains data of different types. You will have to represent that. You will have to like write your own things or use libraries. They are not things that are by default there in the programming language. So I hope the examples are I'm only trying to give you an intuitive understanding of the difference between these two things, but I hope those examples are sufficient. But yes, I think what Modish said is correct. That cat, as I showed it, is not is yeah, it is a string. It is not a number. So it is a different type of data from the previous things we were looking at. We will not be using these in our examples but in any job related to data science that you do, or to relational databases, you will have to come across these two data structures called stacks and queues, because the vast majority of databases actually store data in this way. A stack is literally, the word tells you what it is. So imagine if you had your collection of all newspapers over the last month, and you stack it up on top of your desk. Then if you're a if you're a normal person who then first removes the paper that's on top, then you know that whatever you put last onto the stack is the first one you can get out, right? Otherwise, you'll have to pull something out from the bottom of the stack, which is like it will mess up your stack. So it's not recommended. So you can push something onto a stack, and it always goes on top of what is already there. And then if you pop something out of it, you will always get whatever you put in the last. And that is a data structure called stack. A queue, on the other hand, is again, it's very intuitive. You can think of it like if you're waiting for tickets or something, and there a person who comes first into the queue will be the person to leave for the first. So if you arrived the earliest and you were waiting for your tickets the longest, or you were the first person to enter the queue, then you get your ticket the first, and you leave the queue first. So these two pictures themselves are quite intuitive, I believe. I hope that does not require more explanation. A stack has usually two operations, push and pop, and they always add to one end of the stack. And a queue always has NQ and DQ, and you always remove things from one end of the queue while you add things from the other end of the queue. We will not be using these in the examples, at least today. Maybe the example next Monday you'll have it, but you have to understand why these are important. For example, the list of transactions of your account that your bank maintains is typically a stack, because your transaction from 5 years ago is not something is something they want to keep in their database, but it is not the one they want to easily access. If you log into, for example, your net banking, or you go get your passbook updated, what you will normally get printed are your last few transactions. But on the other hand, the Indian Railway Catering and Tourism Corporation, where you go and book your railway tickets, that one has if you have noticed, if a train is full, it lets you be in a waiting list, and that waiting list is usually managed as a queue. Because of this reason, whoever first got on the waiting list should be the one to get a confirmed ticket first. The other advantage of stacks and queues unlike arrays, but similar to lists, is that each of these elements can be a different type of data. It can be a composite type of data. It doesn't have to be just integer numbers. For example, if you're talking about account transactions, some of your transactions are very routine. For example, they are just your salary getting credited, or your payments to a certain website. Whereas some transactions, for example, will need to contain a lot of information. Maybe it is a refund, and so the person has to explain why exactly there was a refund, or it is an interest being credited by the bank. So they usually add information in the form of text explaining why that is, etc. And so each of these elements can be arbitrarily different, and this is why stacks and queues are used. So just to give you an example, within Collaboratory, that is within Python, if you make a list, for example, you do have an option to, once you have declared a list, you do have an option to treat the list like a stack or a queue, because if you see here, one of the options you'll see in the you'll see pop as an option. So you can pick that and you can run it, and what you get is then last object in the array. If you now pop it again, and you will also notice that after it has been popped, your array 1 is now shorter. So an element has been removed from it. So a list which exists only in Python as a primary data type is, you can think of it as a combination of it has all the features of both an array and a stack. And but these are not things you will find in like C++. I don't know about R. I'm not very proficient with R. But you will notice that a list has features of both a stack and an array. So this now brings us to the next step that I think you need to learn in order to actually work on real data sets that will go into, for example, fraud prevention. That is how to visualize data. So there are, I had earlier explained that some of the methods by which we visualize data are tools such as histograms, scatter plots, and graphs. A histogram is if you have a large, let's say an array or a large stack, a list of numbers corresponding to, let's say, the number of steps you're taking every day as a part of your exercise, or if you're keeping track of your steps using, let's say, a mobile data, or and this is a valuation every day. A histogram counts how many of those entries are in each interval. So the things that quantify a histogram are that it has different bins, each bin has a width, and then the count in a bin is the useful information you get from a histogram. So let's just, as an example, make a histogram in Collaboratory just to visualize it. Here I am now creating an array of size 8,000. So it will contain 8,000 numbers. Those numbers are going to be normally distributed around its mean, which has a value of 175, and a variance of 5. These are numbers I have randomly picked. And so now you can verify that this gdist is now an array. I'm going to print it out for you so you can see it. And you can see that it is an array. You can see each of these numbers you see are in the range that I've specified. And in total, the length of this array is 8,000. So that's what this means. Once again, if you want to call a function, one of the options you can do is you can just look at its signature live in an interactive way. Just highlight it and it will show you what are the options the function will take. So to create a histogram, what I'm using is a module called matplotlib. This should work off the shelf if you use Collaboratory. And the only thing I need to do is just say create a histogram, because I like having my labels, my axes labeled. I have also specified them, but it's not important. Like, you can literally not have either of these, and it will create a histogram for you. So now you will notice that this, you had no control on. It has 1, 2, 3, 4, 5, 6, 7, 8, 9. Just a total of 9 bins. You had no control over how many bins it had. You can choose to specify the number of bins you have this way by typing out the number of bins. Note that while I do that, it gives me suggestions on all the other options I have when I'm making these histograms. So let's now try it with 15 bins, and you see way more bins. Let's try it. Since there are now 80,000 data points, we can actually try 150 bins, and you'll notice that the total number of bins has now increased. Each bin is, there are now in total 150 bins. I'm not going to count them because that would take a long time, but the bins are now proportionally smaller. One of the other things you can do is you can explicitly specify how you want the bins. So let's say you can have the bins between 150 and 280 on interval, 220 on intervals of with, let's say, 300 intervals in between. So 300 bins in between. If you do it that way, it will show you. This is the explicit range. You can change. You can now make it cruder. You can reduce the number of bins, and you get the bin width. So if you reduce the number of bins, you notice that you have only you have more counts per bin, right? You must have noticed that if I give 300 bins, I get the values along the y-axis. The maximum value is rather small, 1,400, whereas if I choose to have 30 bins, it is of the order of, it will be 10 times larger, 14,000.
Sir, are these been what we call in statistics intervals, or is it something else?
Yes, a bin is essentially an interval. Exactly.
Class interval, I mean.
Yes. So
okay.
A histogram is often also called, there is a tool called a frequency polygon, right? And in that it is explicitly called an interval. I'm not 100% sure of why people have histograms and frequency polygons as different things. If you draw a frequency polygon, it will, instead of having this like blocky shape, it will be something that joins the middle of these bins. Now, so if I choose fewer bins, you'll notice that each bins contain more. That's because the array I'm giving it is of a fixed length. We already generated an array of length 80,000, and we're just plotting the same array in different ways. So if you reduce the number of bins, the number of the content in each bin increases, and that is to be expected. So you can also choose each bin to have a different width by, instead of using so you're specifying your bins to be an array. Here you're specifying your bins to be an array, but it is logarithmically distributed. So just to understand the difference between, you know what? I'll share this notebook with you after this class, and you can play around with this by running this within your Google accounts, right? So you can, by just specifying this variable differently, you can choose each bin to have a different length, a different interval size. You can, for example, plot two different histograms in the same plot by just calling it twice. And you can specify a different number of bins for each histogram. You can specify the colors explicitly, etc. You can even make one of them transparent. For example, you'll notice that the green is now above the blue. So if you specify it to be, so these are just tricks within Collaboratory for things to be visual. Now you can see that the blue will jut out through the. So if you make the blue also transparent, you notice that both of them now overlap, and in the overlap region, the colors are more easily visible. You can also set, for example, you will notice now that your X and Y axes are linear. You can pick your Y axis to be logarithmic. I'm not. If you're familiar with what logarithmic binning is, logarithmic intervals are, you'll notice that now it seems, the intervals along the y-axis are spaced logarithmically instead of instead of linearly. So these are all options for visualizing data that are there in Python, which is the language that I'm most familiar with and which will be the one I'm choosing to show examples in. You will find similar options in almost everything, in Mathematica, in MATLAB, I believe in R, also, and Stata, and whatever tools you're using. It's important to understand how to make histograms, how to make scatter plots, etc. Now the other example type of figure you have is something called a scatter plot. So imagine you have the data from, let's say, 100 countries, which you have divided according to different continents, and you notice that the richer countries on average have higher life expectancy. So if you want to see that correlation, one of the ways to do that is to make a scatter plot. When you have a 2 by n array, so it is a two-dimensional array that you have now. You have columns corresponding to 2 bits of data. One is each country's GDP per capita and its life expectancy, and the number of rows you have is for each country separately. So an example of how to make such a figure is, now let us create one array which is just numbers between 0 and 3, and another array which is the square of those numbers plus a random component thrown in, which is normally distributed. And you can now create explicitly something called plt.scatter, and you see a scatter plot. So the quantities that are shown along the x-axis are from this array, and the quantities which are shown along the y-axis are from this array. You can make it, if you just want to see how it will work in terms of cubes, you can do that. Feel free to play with these tools just to understand it better. You can set the scale to be much larger, in which case you'll see that it is now much more spread out. You can control the size of each point using this parameter, but let's change this to 1, and you see much larger points. So this is how you may visualize data in Python. I don't want to give, let's say, do too many more examples live, because I think it's very simple. If you just follow the instructions I've given you, log into Google Colaboratory, start typing in simple bits of code, it will on the fly give you instructions on how to get things to work, and you can make figures like this. We will be using this tool once again when we are working with the real life data set. But the last bit of let's say data visualization that I want to introduce you to is something called a graph, which is very much like a scatter plot, but each data point is joined by a line. So if I were to make that, let's say in Colaboratory, if I replace this scatter with plot, I would get a scatter plot, but it is going to look very ugly because those points are very scattered. See it, because each of the points are joined by a line. But if I now remove this this random term that I've added to each number, you're going to get a very smooth line. So the kind of visualization you choose is really determined by the statistical properties of your data. Because if you're seeing, let's say, if you're visualizing data that is widely spaced along your different axes, it will look nicer as a graph like this. But if you have very closely spaced together data, and it's not really like what you think of as a function, like it's not unique data points along x and y axes, then a scatter plot is better. If you have purely one-dimensional data and you just want to see what is the frequency in each interval, then a histogram is what you want. And these are not the only ways to visualize data. You can make a histogram in higher dimensions, which would mean that you would be looking at like a you can just Google. There are many ways to visualize higher dimensional histograms. There are these things evolve with technology and what our current capabilities are. And for example, while I was preparing for this course, I discovered that in the 70s, when they started having large bits of data, because many aspects of things, they introduced mainframe computers and supercomputers and such powerful computers, but visualization algorithms, etc., had not developed so far. There was machine learning, etc., had not been created. So they had a period where a lot of different fields that employ data science use something called a Chernoff phase. If you have a browser open, just type it out and Google it and see what it is. It's very amusing. It's based on the idea that the human brain is actually very good at telling faces apart. So if you encode data into the shape of a face, then you can visualize it very easily. And so in the 70s, they used to use that to identify different features within data. I don't know much about them, but it's quite fascinating. I do not know any modern application for a Chernoff face. Nothing that I have ever worked with has employed this, but it is an interesting thing that you can read up on. So data visualization is, I introduced you to three basic types of how to see data, which we will be using in our examples. But in general, you can visualize your data in many different ways. You can have 3D contours, etc., which we will probably introduce only in a later module also. And it is something that's evolving with the available technology, because in principle, if you know how to write these bits of code, you can construct arbitrary ways to visualize your data, and it's a question of things being widely accepted and it being useful to you. So now we get to an example of ePayment, and let's look at a specific example. So Kumar is, let's say, a hardworking automobile mechanic. He lives in Worli. Every day he has chai at a local tea shop. He buys lunch at work. He buys groceries on the way back. He pays, for example, his electricity bills automatically with his card. He occasionally spends money at restaurants and in cinema using, so which would normally consist as leisure. And one day, the bank gets a transaction request to pay for a 4,000 rupee bill at a restaurant in Goa. Now, there is a very reasonable case that Kumar is on vacation and this transaction has to go through. In fact, most of us, when we open an account at a bank and we get a debit card or we get a UPI address, ID, the Unified Payments Interface, which is very popular in India now, we literally want to be able to spend money in a diverse set of places with it. So just because it is far from where he has normally uses his payments methods does not mean that it is a non-desirable transaction. In fact, we do not know. We don't know if Kumar is on vacation in Goa and he's asking to pay a 4,000 rupees bill, or if his phone or his debit card has been stolen by somebody. So the way to try and identify what the case is to go by the features of the data that go with each transaction. So a transaction will correspond to, let's say, a column, a row in a table in which there is total amount of money. The transaction will have the amount of money with that transaction, and it will have a timestamp at what time was the transaction made. It will most probably contain GPS coordinates, because most apps that handle payments explicitly require it. So those are the bits of data that go with each transaction. Now, people who have access to that data, they can compare it against your other transactions and add it up to get ideas like what is the total amount of money spent on that day, the number of transactions on that day, etc., which are with derived features. You would an individual transaction will not contain a feature such as the total amount of money spent on that day or the number of transactions on that day. But if you have access to the database or transactions, these are things you can easily extract from the database. And one of the ways fraudulent activities can usually be caught is that people, if they steal somebody's debit card or they have stolen their password or etc., they'll try to spend as much as possible in a short space of time. So this will allow us to identify transactions. So Subodh in the previous lectures has taught you a sequence of, let's say, sophisticated statistical ideas, which has given you a very strong foundation. And I believe he has taught you what is called the normal distribution. As you see, a normal distribution is characterized by where its center is. So in the example I was showing you in collaboratory, the center was placed at 175 because I literally put that as the location. Then it is the width around it, which is known as the standard deviation. So the mu is where the center is. The standard deviation is sigma, and you can construct a measure of how far each transaction is from the typical size of transactions of a person, known as a z-score. And this is it is an extremely simple statistical tool or a score for a transaction of this kind. It explicitly assumes that the distributions are normally normal. That is, the transaction amounts are distributed normally. This might not be the case. For example, if you're looking at the timestamps of transaction, that is more or less more likely to be evenly distributed during the day and not at night, etc. So it will not have this shape. So you should be careful about where you use such as this statistical method. But for things such as your transaction value, which may be normally distributed, or the number of transactions per day, etc., which may be normally distributed, this is an excellent criteria. What it basically quantifies is how far from typical behavior is it. So if an object is just 1 sigma away from typical behavior, that is, if the z-score value is 1 or -1, then it means that it falls in this interval and there is nothing unexpected happening. Whereas if a z-score value is 6, then this is a very unusually large transaction that is going on, and you need to pay closer attention. Now, most of the systems that you're working with do not use a simple method like this to just reject a transaction, because, like I said, everyone wants to be able to make larger transactions. But what they will do is usually to trigger an additional step of authentication. In the olden days, when credit cards, before the internet, when credit card networks were still there, you would immediately get a phone call sometimes asking if you have made such a transaction. Nowadays, what will happen usually is you have to enter an OTP, which is sent to your phone. And you may have noticed that if you are using a card, on some transactions, it does not ask for your OTP. On some transactions, it does ask for your OTP. And it's usually based on a test like this, known as a z-score. So this is an extremely simple statistical test, which is widely used across the industry. A typical process for identifying if a transaction is fraudulent or not, or when you initiate a transaction, is represented by what I'll call here a flow chart. So normally you will initiate a transaction, and then what happens is the system will automatically, because code will let you automate things, access the database of all your past transactions, and it will do an ECZ test. So it may be usually with a value of just of 3. So if the z test is less than 3 or greater than -3, which is it falls in the central region where you think it is typical behavior, it will automatically approve the transaction and it is over. But on the other hand, if the z test fails, it will send you to a second step of authentication where you have another process which is running automatically, which also has access to the database, which will now compare an appropriate test, which might once again be a z-test, or it could be any number of tests that I will introduce later. And again, if you pass that test, it is approved, or if you fail the test, then it is sent to a more detailed process where more features are employed to once again make a decision on whether to pass or fail the transaction. And based on that, the transaction is finally either approved or rejected. The second test often can contain information that was taken in as part of the, let's say, the input step of this, which was triggered using the first test. For example, you may enter an OTP, but if you have reasons, if the OTP was delayed, let's say if it was entered after a 5-minute long wait, then you have reasons to believe that the person may be, he may not have access to the actual phone, and it might actually be a fraudulent transaction. So that is the sort of situation that you test for in such a test. And what I have illustrated here is something called a flow chart, it is a very common concept if you're studying programming or algorithms, or also processes such as data science processes. If you start a data science job and you are working on a project is most often organized in its documentation as a flow chart. It was once again, these are tools that are evolving with time. These shapes usually determine what kind of a process is happening. So this is usually a starting block. One with curves on both sides is usually a stopping block. Anything in which the process flow diverges into two possible futures, where depending upon some criterion, failing or passing is now this shape. I believe the shape is called a rhombus. So a rhombus shape determines if a decision is to be made, and it has multiple possible outcomes. Anything that requires accessing an external database usually has these sort of symbols. These are not stringent rules. These are all evolving depending upon the organization whose data science processing method you're looking. Maybe some of them will just use the same shape for everything. So don't take these too stringently, but sometimes when an external input is solicited in a step, it will have like a sloped roof, etc. It will have this shape. This is a quadrilateral that is not without parallel sides. So it's a rather arbitrary quadrilateral, but with this shape. And quite often, this flow chart allows you to see the entire data science process that happens behind it in a very conceptual way to allow you to write down. Yes?
So basically the idea behind detecting the fraud is that, is it that we will look at the value? I mean, if value is, if the transaction or the data of that particular transaction is deviated from mean beyond the Z critical value. If that is beyond...
Could you repeat that last bit again, the critical value bit?
And critical, I mean Z value that is beyond the, I mean that standard deviation, like 95%, 99%, if it is deviated 99% in normal distribution, if it is beyond 99%, then it can be a case of fraud. So
yes.
I mean,
so for example, in the Z test, the value of 3 corresponds to 3 sigma, which for a standard deviation is 99.9%.
Oh.
Right? I thought it was 99.7%, but yeah. This might be like a 2-sided versus 1-sided thing. Like it might be telling you everything on this side, but not on this side, etc. So, so a Z score greater than, the critical value. So what the terminology that you're calling critical value corresponds to the choice of 3 here. It's an arbitrary choice, and
Yes, sir. Yes.
as I'm about to explain it, it will be actually varied. Like it's not a fixed choice. And to understand why, so this flow chart now allows you to visualize how exactly the process will happen, and decide how to optimize your process. But before that, let me just revisit. So Subodh has already made you understand this concept very rigorously when he was talking about the false positivity and the false negativity rate of tests and the true prevalence, etc. But within the language of hypothesis testing, there are these are called what is called a type 1 error and a type 2 error. So let us imagine a situation where a transaction is actually is in reality fraudulent. Let us imagine a situation in which a transaction is in reality not fraudulent, but if you now classify it as fraudulent, that is called a type 1 error. And the probability of making such an error, let's call it alpha for the time being. We can fix it later. The other situation is where the transaction is actually not fraudulent, but the transaction is actually fraudulent, but you classify it as not fraudulent, and that is a type 2 error, wherein it's a false negative. In reality, it is positive for fraud, but you're classifying it as not a fraud event. So you're classifying it as a false negative, and the probability of that, you can assign it as beta. Then you know that because these are independent events, the true the reality of what a situation is, then the probability of you not making an error is 1 minus beta, and here in that case is 1 minus alpha. So there are 2 types of errors, and now that you have terms to describe what those errors are, using a flow chart of the kind I described earlier, you can write down what is called a cost function. Now let us actually to take you step by step through the process of writing down a cost function. I'm going to simplify this. This elaborate machine learning or involved process in the future, that is a 3rd step triggered after your 2nd step of authentication does not exist. Let's just remove that. So we have this 2-step process wherein you have first a z-test and you have second some other appropriate test. And what happens is, if your z-test fails, you send it to your 2nd step of authentication. If that also fails, you reject. And if it passes, you approve the transaction. It's a very simple process. You have 2 numbers, which you can think of as analogous to Subodh's example of the actual prevalence of infections among the population. Here is the prevalence of fraudulent transactions, which is, you can call it F. So if it is 0.05, it means 5% of all transactions are fraudulent. If it is 0.2, it means 20% of all transactions are fraudulent. Then normal transactions then are the remaining, which is 95% or 80% in the other case. So it is 0.95 or 0.8. You have the total amount for a transaction, which is a transaction amount. And now you can write down the 2 types of situations. The total cost as the probability that the transaction is fraudulent times the probability that you misidentify it as a normal transaction, that is a false negative, and the probability that you actually identify it as a fraudulent transaction in the first step, and then you send it to the 2nd step. So the 2nd step, because you need to associate a cost associated with doing the 2nd step, because let us say in the case of the example where we are talking about getting an OTP, your bank has to have a deal with the mobile operator to send SMSs, and they're probably paying them for it. So that has a cost. That is C2, which comes in only if the second step has been triggered, and then there is the probability of a false negative in the second test also multiplied by the amount. And here the amount is multiplied because you just make an assumption. I'll come to it again, that if the transaction is completely fraudulent, then you cannot recover the money at all, which is usually not the case, because in hindsight you find out the transaction is fraudulent, then you can complain to the police, or there are bank tribunals, etc. you can go to for help. And that is the case where the transaction is actually fraudulent. If the transaction is not fraudulent, you have no loss if if you just let it pass in the first round. But if you actually send it to the second step, there is a notional cost of the second step again, and there may be some notional cost even if you send it, even if you approve the transaction, because there is a notional cost if you fail the transaction, if it is not a fraudulent transaction, because nobody likes too many failed transactions. You want your payment to work. I'll explain to you why it is notional, because it is a complicated thing. It is set by the market later on, so it's something for the person to decide. But you have also the probability that you don't fail the transaction. You let it pass, which is given by 1 minus alpha, because alpha is your probability of a false positive. In which case, you again have the cost of doing the second step, and then you have the related cost of the fact that this notional cost of you failing the transaction. Now, let me just once explain to you in detail what these things are. The cost function optimization is very contextual. For example, F is different depending upon country, type of transaction, etc. For example, when Subodh and I were living in Denmark, we would quite often notice that you just have to wave your card at something and the payment just goes through. It usually doesn't even ask for a PIN. And that is because Denmark is a very homogeneous country, a very small number of people. Crime and fraudulent transactions are rather low, I believe. So this F is a very small number. And so you optimize for different things. Whereas it is possible. I don't know we will actually look at reasonable values of F for different countries in our next week's exercise. It is possible in India that F is is a much larger number. C2 may be 0 in the sense the cost of doing this additional step of authentication may be essentially 0. For example, the cost of doing an SMS is essentially negligible, and if as a bank the contract you have with the mobile service provider is to have an infinite number of SMSs, then there is no cost to doing the additional step. But there may be like a notional cost based on market considerations, which is that you notice that if you use HSBC, you always have to go to second authentication step, whereas if you use ICICI Bank, it's quite often not the case. And for some reason, if you believe everything else is like they're both equally safe banks, the risk of you losing your money is lower than based on a purely matter of convenience. You may choose to make C2 non-zero, even though the actual cost of doing a second step may be 0, because you don't want to inconvenience your consumers. So this is something that a person who understands the market that you're up against has to set by hand. The cost of a failed transaction is essentially purely set by the market, because what you or I may have noticed is that if you make a UPI transaction and your transaction fails, then I will talk to you in 20 minutes or so, because I'm on a call. Sorry. Yeah. If you set your transaction let's say if your transaction keeps failing, but it is happening only mostly for one bank and not for the other, again, you may choose to switch banks. So these are terms that you have to decide based on these sort of complex considerations. If, for example, you choose to have this additional step, which requires machine learning and a full-fledged consideration of what you consider all the features of your data, then a third level of costs will depend on how many employees you have working on this problem, how much computational resources you're calling a server, the additional time, the additional delay to the transaction, etc. So these terms really are contextually determined. Once we fix these terms based on these considerations, what we are left with is really the false positivity and false negativity rates of the first of these two steps of the test, which we can really just put in by design. So, for example, the false positivity rate of a z-score test really is determined purely by what value of this critical value, as Modish described it, you choose. If you choose the critical value to be 2, your false positivity rate will be much higher than if you choose your critical value to
Sir, actually, what happens is in what we do in statistics, or what I have read in research hypothesis in regarding this. So I found that they call it significance level, and that 5% level, it is 95% value that is for 1.96 वो जो normal distribution पे आता है. तो 99 पे वो Z क्रिटिकल वैल्यू बोलते हैं. तब होती है कि जब आपका सिग्निफिकेंस लेवल 1% के आसपास होता है. तो वो इस वजह से है सर. यस सर, दैट्स ऑल. थैंक यू.
So yes, thanks Modish for making that very clear. What he's basically saying is that if you pick, for example, this value to be 2, then you have a false positivity rate of explicitly the area under this curve on this side, right? Which is given by 1 minus 97.7%. So these are terms you fix by just deciding how you want the critical value to be. And so what you normally do is you optimize a cost function. You don't want to have too many losses, so you reduce. You find the values of beta 1, beta 2, etc. by alpha 1, alpha 2, etc. by minimizing this function. So to minimize a function, if you know calculus, the simplest way is to just take a derivative and set it to 0 and see how to evaluate it. But you can also just, on a computer, you can minimize it by just trying a large number of values. There are iterative ways to minimize a function. But a cost function defined in this way and constructed through an algorithmic process of splitting down a process is really at the core of what you would consider much of your applications in machine learning, in data science, in real life, because you can Google this within, for example, regressions or neural networks or predictive algorithms. They have very formal definitions of what a cost function is, which in a process like this, which employs data science at different steps, this cost function is constructed intuitively. And like I said, it is very contextual. It has to be chosen based on what it is that you're looking for. So it's actually 5 o'clock, and I had planned for this to be a 1-hour lecture, and I will. I also have meetings from 5:30 onwards, so I have to stop now. But this is the concluding slide, where I will just summarize that we have introduced rudimentary features of the mechanisms operating to make sure you're not defrauded. And in the process, we have introduced some basic data structures, how to visualize data, the concept of dimensionality of data, what is a type 1 and type 2 error, and how to construct a cost function for a very, very simple thing using a flowchart. Now, I used a flowchart to basically make the the step of going from this process to this function look kind of explicit. If some of you, it really depends on the people. Some people can really just if you tell them the sequence of steps, from there they can just write it down. But it's nice to visualize your things as a flow chart in order to write down the cost function. And almost all problems in machine learning and statistics that you use for data science will in some way or the other be the minimization of a cost function. Any real life example of using machine learning that you have in any like job or on the fly example you work with will be using a cost function. So what I will do is to familiarize yourself with these concepts, I will upload a problem set, and which will also involve making some plots, how to visualize data, making some specific kind of plots using the tools I have introduced you to. I will upload this problem set latest by tomorrow evening, and then you can work that out over tomorrow, day after, and Friday, and then the Friday question and answer session, which I believe is either at 5 or at 6 p.m. I'm not 100% sure. We can discuss that problem set, and then on next Monday's next Monday, we will use these tools to look into some real life data set, which is one data set we will look into is found on this link on Kaggle called credit card fraud. It is apparently a real data set from a bank which has been sufficiently anonymized. And then I will also show you what a data set from the National Payments Corporation of India will look like. I cannot show you a real data set because that would be a violation of privacy. So it will be it will have the same kind of rows and columns as they store, but it will be like simulated data. Because I tried convincing them that I could anonymize the data, but no one's agreeing to that because this is a public sector operation. They are very conservative with respect to such things. So these two examples we will look at next Monday. But for today, I think that's it. Thank you. So
thank you,
does
sir.
anyone have any immediate questions right now, or?
Sir, we will ask on Friday.
Sure.
Yeah.
Did you find this level too rudimentary? Because last time we had a question. I had a question and answer session in which I connected. The majority of students were engineering graduates, so I would have thought this is too elementary. But then this time there are also people who have not. So I hope you're not finding this rudimentary, and I hope you're finding my explanation of how to construct things useful.
Sir, it is good, sir. We are able to understand.
Okay, thank you. So,
sir, can we import data from Excel or some other file like Google Sheet or something like that into Python?
Sure. I mean, if you just if you type out the words you said out like import data from Excel to Python, you will see multiple ways. One of the ways would be just to save your Excel file as a comma separated value file, and then you can import it using NumPy. I can maybe add an example on this in the problem set or in a Friday session. But these
okay. Sir, one more question, sir. In our social sciences research, what happens is we have so many variables, like factors. We call them factors. Sir, are you able to hear?
No, your audio is not extremely clear, so I have to.
Just wait, sir. Wait. I'll just try to.
Sir, can you hear me now? Sir, can you hear me now?
Yes. better.
Sir, in social science research, what happens is there are factors like one dependent factor, a variable depends upon some other two, three, four, five uh, other variables.
Sure.
So these variables, like we said, you said in there are they can be called as vectors. In our work we call them factors. So that kind of factors can also be analyzed, I guess, in Python.
Yes. Yeah. In Python, it's a general purpose programming language. You can do almost anything. Like I would be willing to bet money that if someone said, "Here is a thing that I have which I can do in this language. I cannot do it in Python." I will be able to bet money that I can do it in Python. That's
Okay,
how
okay, okay,
confident I am of doing things in Python. But so you can do almost anything in Python. If your specific example of using factors or dependent variables, etc., if you can send me a more well-defined question in an email, I can actually help you write an example in Python.
okay.
So
So, sir, I wanted to know. I mean, it is worth to uh, invest so much time to learning in Python rather than using some other tool like SPSS or some other. So that there are so many tools, sir. I am confused. Which software to use, which not to use. So Python would be sufficient if we learn Python well.
yes, if
I
you
think
want, uh,
if you learn Python only,
yes,
I think for analysis purpose.
I agree. And also, I mean, there is the singular thing about Python, which is that it is the only thing. Like, I don't know how to teach you. I don't know SPSS or Stata. I have used R once. I'm not familiar with it. So Python is really the only thing for data science that is convenient that I can teach you.
Okay,
There
okay,
is
sir.
something called root in C++, which I can help you with. But these are the only things I know.
ओके नो सर
But
आई वो सर हमारे को ना अभी ज़रूरत पड़ेगी ना जैसे आगे 2-3 साल तो इतने सारे सॉफ्टवेयर है कि पता ही नहीं चलता कि कौन सा यूज़ करे और फिर सीखना भी है फिर वो उसका एक्सेस भी नहीं मिलता फिर कई कई प्रॉब्लम्स है तो दैट्स व्हाई आई वाज आस्किंग कि पाइथन विल बी वर्थ टू लर्न
yes, in fact, yes. Python is free. It is open source. You learn it. I mean, I don't know if you're asking for my advice, what you should learn. It is the I would recommend this. But I would also recommend that you understand concepts in a programming language independent way, so that when you are confronted with a new programming language, all you need to do is like Google how it works, and then you can implement your own ideas. Because um, I don't know if what I said is a bit too like I'm just saying the ideas that we are using are quite independent of programming languages. So
ओके ओके
understand them that way and just understand how to implement it in one tool or programming language, and that's sufficient.
ओके सर ओके थैंक यू वेरी मच
Sure. So if I'm always reachable by email for any questions you have. For example, you can if you can try working out arbitrarily more complicated cost functions or something of that sort. There will be a few in the problem set I will upload tomorrow. But yeah, if you have any questions, feel free to reach out to me. If not, I will. Is it okay if I disconnect now or?
यस सर यस